In Chapter 4, we introduced the laws of Newton and the concepts behind those laws of Newton. We, in particular, looked at the second law, which was our quantitative calculation of force as it relates to mass and acceleration. And we said that the forces acting on the mass are forces that will be perhaps pushes or pulls, could be gravity, could be U, could be strings or springs or cables, any kind of force, either contact or non-contact force. In particular, one force that we want to focus on specifically is the force of friction. And this will enable us to bring into our analysis and study the common force of friction which acts on everything. And this force of friction essentially eats up the energy objects have and creates unuseful heat as a result. So let's take a look at force of friction here. First of all, what do we know about friction? Well, friction causes objects to slow down. You know that if you release the accelerator pedal in your car, it's going to subsequently roll to a stop. And that is due to not only the friction with the road, but some of the internal friction of the moving parts. Where does this energy go that the car possessed? You'll see later on in Chapter 5 as we define kinetic energy of motion, the car has energy because it has mass and it's moving with a velocity. So it does possess energy. This energy that the car possessed has been dissipated in the form of heat primarily. And so friction degrades or essentially diminishes an object's energy and becomes a non-useful random heat. In order to understand friction, we need to take a look at it empirically, and that means from experiment. And we want to develop a relationship from experimental measurements. In this diagram, we are showing simply an object on a surface, and the object has a downward weight, shown here as mg. And then, of course, because the object's weight is pushing down on the floor is pushing back up with a normal force, equal and opposite to that weight in this case. And if we are applying a force to the right, where the object is we're attempting to move the object, and there is a oppositely directed resistance due to the friction force acting to the left. This object is at rest, then as we apply the force to the right, the friction is resisting us, and if we do not apply a sufficient amount of force to overcome that friction, the object will not move. Now, on a fundamental level, friction is a result of microscopic imperfections, micro welds, and here we see just a couple of electron photomicrographs showing the surface of a metallic substance. So you can imagine having two pieces of this material. You're attempting to slide one over the other, and these irregular hills and valleys on a microscopic scale are impeding one another and having to essentially break little pieces of these, perhaps micro welds forming if they're close together, and there's been some diffusion across between the two surfaces. And so friction fundamentally is a very difficult problem because in a small area such as this, you may have millions and millions of contact points and potential microwelds, and you would have to be able to write equations of motion of each one of those. And then imagine you have then now a square inch of surface area with literally billions and billions of these interactions going on. Well, that's far too many equations to try to solve, to try to derive a relationship for friction based on what we call first principles. Fortunately, from experiment, we are able to perform some measurements using, say, an object on a table or an object on any surface, and measure how much force it takes by pulling on that object attached to a spring, how much force it takes to just break that object free and get it moving. And if we plot the applied force, which essentially is we're resisting friction, so if we apply a force to the object, and as that force increases, the frictional force increases along with that. Okay, so we're applying a force, and we see the resistance of friction increases in direct proportion. At some point, we know that the object will now begin to move, and therefore we have reached the maximum of that frictional force. We have overcome it, and now the object is in motion. That's a kinetic situation, kinetic meaning motion, and for right now we want to focus on before it starts moving, but just reaching that point of impending motion. As a result of the measured force that we have to apply to the object, and knowing that the object is resting on a level surface, and therefore there is a normal force acting on the object from the surface, we can find there's a relationship between the force of friction that we're trying to overcome and the force that the surface is exerting on the object, and that ratio of that force, frictional force, to the normal force is a constant. Given the symbol mu, that's mu, the Greek lowercase m, and so we're subscripted this with an s to indicate that this is for a static situation where the object is not moving. Okay, so this is friction associated with an object not moving but being influenced by a force up to that point where the object is about to break free. So the coefficient of static friction is what mu is, and generally it varies between 0 and 1 or 2. The lower the value of the coefficient, the lower the frictional force. In other words, the more easily the object is moved. The higher value, the more difficult it is to move. A car tire on a warm, sort of sticky asphalt pavement has a high coefficient, meaning it's sticking to the road more easily than, say, a tire on a road covered with a slick of water. There's a low value of mu. So we're going to use this equation as an expression of the frictional force. What that means is that anytime friction is involved in a problem, and our goal is to solve Newton's second law, F equals ma, then we must look at the object of mass m and ask the question, is friction present? And if it is present, then we are to use an expression like this for a static case, or an expression similar to this for the kinetic case, which we'll look at right now. But let's look at an example of static friction. Here we're told that we have a 2 kilogram block on a surface, and it requires 2 newtons of applied force to just get it moving. So in other words, it's right at that brink of not moving, but right about to begin moving. So it's at that point where this is the maximum frictional force that's resisting this motion, and we are applying just the right force to break this object free. but it's not yet moving because we want to maintain a static situation. So what we know is the mass of the object is 2 kilograms. We apply 2 newtons of force, and we would like to know what is the coefficient of friction in this case. Okay, and we know that the velocity of the object is 0, clearly. So we're just simply applying our relationship that the frictional force is equal to the coefficient of friction, that's what we're looking for, times the normal force. Now recall when we dealt with our objects on surfaces and we drew free body diagrams that the normal force for an object on a level surface was opposite to the weight, and the normal force was equal to the weight, but it was directed upward. So the normal force is the weight of the object, which is mass times gravity, 2 kilograms times 9.8 meters per second squared. That gives you 19.6 newtons of weight, which means the normal force is exactly 19.6 newtons upward. And we are applying a 2 newton force to overcome friction. So we have 2 newtons equals mu, the coefficient, times 19.6 newtons. And then we can divide those two. Here we have 2 newtons divided by the weight mg, 2 times 9.8, to get a coefficient of friction of 0.1, approximately. Okay. Now, that's static friction. That is friction that is acting on the object prior to its beginning to move. Once the object is moving and there's some momentum associated with it, the inertia has been overcome, the inertia resisting motion, and now it possesses momentum, the object is going to more easily move. Imagine if you're sliding one surface over another and there are hills and valleys that are impeding, they're shearing off more easily. So it doesn't take quite as much force to keep the object moving once it's moving that it did to start it moving by overcoming friction. So because the resistance is less, we're going to find that the friction associated with sliding is actually lower than the friction associated with static or at rest motion. The word kinetic derives from the Greek word kinema, meaning motion, and so we refer to this friction as kinetic friction as opposed to static friction. It looks like this. Here's the graph that we saw before where we were applying a force and the frictional force was rising in direct proportion to the applied force. We reached a maximum point at which the object would now begin to move, and notice that the force of friction has dropped to a value lower than the maximum force in the static case, dropped down to here, which is less frictional force, and that value is now constant acting. So we have different coefficients, the static coefficient representing this higher value and the kinetic coefficient representing this lower value. So let's take a look at this. For instance, the principle behind anti-lock brakes is such that we don't want the wheels to lock, because once the wheels lock, the car's wheels are skidding, sliding over the road surface, which is a kinetic relationship between the tire and the road surface, as opposed to when they're rolling, that's a static relationship. You have to think about that for a moment, but a tire that's rolling, if you think of a perfect circle and being the tangent point to the circle being in contact with the road, there is no relative velocity between those 2 points. In other words, the point of contact with the tire with the road, those 2 points are at rest as the tire rolls over the surface. So a tire that is rolling is actually a static friction situation. A tire that is skidding is a kinetic friction situation. So we want the tires to roll because there's higher friction involved there. You will stop quicker as long as the tires continue to roll. Once the brakes lock and the tires are locked and not rotating, the friction actually is less between the tire and the road, and it will take a longer distance for you to come to a stop. So here's an example. The car is moving at 25 meters per second, slams on the brakes. The static coefficient is 1.2, but the kinetic is 0.85. How far will the car slide? We have an error in this problem, by the way. 25 meters per second is the velocity. We want to come to a stop. The static coefficient listed here is 0.4, which obviously doesn't match the 1.2 that was listed here. We'd like to know x. How far will it take to slide? Equations we're going to use are our kinematic equation here to solve for the acceleration. Plug that acceleration into here, knowing the frictional force is mu times n, and determine the value of x. That's the pathway. So notice that we have solved for x in our kinematic equation. We've plugged in for acceleration, F over m. Force responsible for the object decelerating, because it's going to have negative acceleration, is a frictional force. Frictional force is the coefficient times the normal force, which is the weight. And therefore, notice the masses cancel out, and we're left with 2 mu g in the denominator. So there's our velocity squared, 2 times, and again, this was the kinetic coefficient of friction that was stated in the problem, times g. And notice this will take 54 meters at this 25 meter per second speed to stop under this kinetic coefficient of friction of 0.85. 25 meters per second is approximately 55 miles an hour, and obviously 54 meters is just a little shy of 170 feet. And so under these conditions, and when the coefficient of kinetic friction is 0.85, we're going to slide 170 feet. Now let's apply the same information to a non-skid situation where the tires keep rotating and we have anti-lock brakes. In which case we take the same derivation, we have the same ending point. You'll notice we have the same starting velocity, and then 2 mu g. Again, this should be 1.2, shouldn't it? Because that's the static coefficient of friction. So we need to change that to 1.2. And as a result, we find that we have actually reduced the distance that we have slid from 54 meters to 37.5. So if the pavement, this is the normal relationship between a dry pavement where 1.2 is the static and 0.85 is the kinetic. Imagine if the pavement were wet and the kinetic coefficient of friction was actually reduced from 0.85 down to 0.47. That would reduce the denominator here, which would make this term even bigger, and we would find it would take 75 meters to stop, or over 225 feet. So making sure that the brakes, the wheels don't lock in a rapid stop ensures that you will stop quicker. Let's take just a brief look here at the relationship between frictional force and normal force. Since the frictional force is calculated from the coefficient times the normal force, are there circumstances where the normal force is reduced and therefore the friction is reduced? And of course, The answer to that is yes. Imagine here shown we're lifting up on this box. Therefore, the box is not pressing down into the surface with as much force. Therefore, the surface is not responding back, reacting back with as much normal force. So whereas normally on a level surface, the normal force is the downward weight, if someone lifts up on the object, that will reduce the normal force acting on the object due to the surface. If the force of friction is proportional to the normal force, then if the normal force is reduced, then the frictional force will be reduced. Think of it as these hills and valleys, small micro hills and valleys, are not being pushed together as severely. Here's an example using our concept of a free body diagram that we talked about when solving problems in Newton's laws. Notice here we have the person lifting is expressed by the capital T symbol. That T, because recall that we use T for tension, and this person is holding onto the block with a string. So we have tension in the string acting upward, the weight of the object acting downward, and then the normal force is the surface response as a result of the difference between these two. Notice that the normal force acts upward, the tension acts upward, and those two equal the downward weight. So that means that in fact the normal force, which without the person pulling on it would be just the weight, now it's the weight less the amount the person is pulling on. So actually the surface is reacting with a lower reaction when a person is lifting up on this box. If the tension exerted by the person is at some angle other than straight up, then we would need to find out how much of that force is pulling straight up and how much is pulling to the right or left. In other words, we need to decompose that into components. Here's an example of that. Here we see a person that is said to be pulling a crate, and we know the weight of the crate is 300 newtons. Remember, that's the product of mass times gravity. mg is the weight. So we have here, we're told that mg equals 300. Right? So that's one of our knowns. We're also told that person is pulling at a 37-degree angle to the ground. So imagine having a 300 Newton box on the floor, you have a string attached to it, and you're pulling it up at an angle of 37 degrees. The box and the floor have a coefficient of friction of 0.6. Okay, and that's static friction. And we'd like to know how much tension must we exert to get the box just moving. So it's not moving yet, it's static, and we are wanting to get it moving. So we don't know what tension we need to exert, but we do know that friction is defined as mu times n, and that all forces must balance because presently the object is not moving. So all the forces pulling right and left and up and down must balance each other out. So let's look at these. Here's our representation. We have the weight of the box. We have friction acting backward. We have the normal force. And we have the person exerting the tension. And that can be decomposed into the portion pulling to the right and the portion lifting up. So the portion pulling to the right, the horizontal portion of the tension, is T cosine theta. The portion of the tension pulling straight up is T sine theta. So in the vertical direction, we have the normal force acting upward, the portion of the tension acting upward, and the downward weight, and those have to equal 0 because the object is not moving vertically. So there's no acceleration in the vertical direction. That shows us that the normal force is actually the difference between the weight and the portion of the tension in the vertical direction. Okay? So you notice if the tension weren't there, this would just be normal force equals weight. And if the tension were pulling straight up, then the sine of theta would be 1, sine of 90 degrees. So anytime that the tension is pulling at an angle other than straight up or horizontally, we're going to have a component of this tension acting in the vertical direction. Now, in the horizontal direction, we see that the tension component to the right, T cosine theta, is being resisted by the friction to the left. And since it's not moving, those two forces have to sum to 0. So we can plug in here for the fact that then T cosine theta is equal to the frictional force. That comes from up here. We take the frictional force to the right side of this equation, becomes plus F. So we get T cosine theta equals F. But F is mu times N. That's just a definition, isn't it? But we found out that N for this case was W T sine theta. So here we have an equation T cosine theta equals mu W T sine theta. So this means that this was our equation we'd finished up in the previous slide. T sine theta, T cosine theta equals mu W T sine theta. Remember where we want to go here. We're trying to find out what tension we need to exert to just barely break this object free and make it move. So we're trying to solve this equation for T. So notice we've collected the terms that involve T on the left-hand side, factored T out, divided the parentheses portion under the right-hand side. Now we're plugging in our numbers, okay, and coming down to finally a solution. That it takes 154 newtons acting at a 30 degree angle, for this object to just break the object free and start it moving. So we'll do more of these problems when we look at the applications portion of Chapter 4 in problem solving.